So today we will talk about the advanced engineered frac design, FracGuru workflow that we put together for the unconventional development and hydraulic fracture optimization purposes. So just a quick introduction. So Oscar did a fantastic job introducing us. So basically Subsurface Dynamics is advanced reservoir engineering consulting firm with the main focus in integrated studies, technology development, and automation. So we have experience operating in over 20 countries around the globe. So we had extensive experience in North America, South America, Europe, Russia, all the way to Australia. And today, what I'd like to focus on is I'd like to focus on unconventional resources and hydraulic fracture optimization work. So basically, as we are talking about the unconventional, the only economic way to extract our hydrocarbons is to employ very significant hydraulic fracturing techniques. And when we're talking about hydraulic fracturing, the key measure that we're using is the economic viability of the process, because the hydraulic fracturing is extremely expensive operation. So the more efficient you can pump your wells, the more efficient you can complete the wells, the better you off in your development program, and the better your company will perform. So, and as demand rose from the industry, we put together a FracGuru workflow with the key features to address hydraulic fracture design, completion optimization, well placement optimization, well spacing optimization, production forecasting, and field development planning. So what kind of problems are we trying to solve? So basically, the key problems that we're trying to solve today is detrimental frac heats, underperforming child wells, and child wells are the wells that were completed as a second generation wells where we already have existing depletion and existing production in the area, pressure depletion impacts, damaged parent wells, and overstimulated reservoirs, and capex overrun.
Sorry, Dimitri, sometimes kind of the sound decreases a little bit, the volume.
Just give me 1 second. I think I know.
Todos se escuchan bien, si por favor nos cuentan. Y
si
alguna pregunta, siéntanse también libres de compartir sus preguntas por el chat, y Daniel o Sol estarán moderando y respondiendo a las preguntas, o Dimitri directamente. Gracias.
Is it better now?
Yes, yeah.
Okay, fantastic. So basically, and if we look at this workflow in general, so it basically we call it the integrated reservoir development workflow for multi-well hydraulic fracture design optimization, or FracGuru, and it ties together all the component of the static modeling, so geological and geomechanical modeling, coupled flow and geomechanical simulation, hydraulic fracture modeling, and hydraulic fracture modeling and optimization in an iterative process. And of course, during the studies like this, we generate hundreds and hundreds of different realizations. So we're heavily relying on the data analytics and statistical analysis to basically help us converge faster and help us to come up with a better solution in a given period of time. So this workflow is covering engineering component of the work, but at the same time, through our partnership with Icon Science, we can extend it further and we can fully integrate advanced geomechanics, seismic conversion, estimation of 1D and 3D in situ stresses, just to enrich the geomechanical and geological model before we go into the optimization study. So, and just to go through the workflow a little bit. So the first step, of course, is the most important step. As we all know, and as unconventional resources matured, the community or operators and service community, they realized that the key drivers of the fracture propagation and fracture geometry that we generate within the reservoir is, in fact, our geomechanics and the stress field within the area of interest. So as a step one of all these studies, we perform a full cycle geomechanical modeling and model calibration for the implicit fracture modeling. So basically, it all starts. It can be different, depends on the kind of data sets you have. It can be as simple as 1D geomechanics, where basically on the few acoustic logs that we have in the area, we can derive our mechanical and stress properties. And then we will expand it to the 3D model, and we run it through the full cycle calibration. So typically, the geomechanical model is being calibrated to the T-feeds, some destructive lab tests, and core and logs that are available in the area. But basically, the minimum, the absolute minimum that we have to derive the mechanical and stress properties would be the acoustic logs or acoustic measurements, and at least 1 or 2 D feeds in the area, so we can actually calibrate it to the downhole measurements. Then, just to emphasize what kind of complexity are we dealing when we're talking about the unconventional resources, and what kind of process we're trying to capture. So this is the gun barrel view of, on the right side, you will see the parent wells. So this is the wells of the first generation that produces depletion. Then on the left, you have a multi-bench second generation development. So basically, in order for us to forecast or predict or optimize the fracs, we need to account for the depletion. Then we need to account interaction between the depletion and the child well fracs. Then we need to account for the interaction between the depletion and the second bench fracs. Then we need to take into account the interaction, like well-to-well interaction. Then we need to take into account bench-to-bench interaction. And on top of that, we also need to take into account stage-to-stage interaction between the fracs, because all those components will be extremely important when we're talking about the completion optimization. So the process itself is extremely complex, and that's why we use the physics-based methods, because basically when we're talking about the complexity like this, the data-driven methods, they cannot reliably predict or forecast the, or reliably optimize the hydraulic fracturing process. So then there is a lot of talks about how we can basically run away and or optimize the fracs on the 1 or 2 stages, and then apply and propagate it for the full wellbore. So this is the good example. We say no, so we perform all modeling on the full wellbore. And the reason why is because this slide is a great illustration of what's happening. So basically, what you see over here is on the x-axis, you see the stage number and the cluster number. And it basically displays the fracture height for each and every stage along the horizontal length of the wellbore. So, and as you can see over here, and on y-axis you have a frac height. And if you, as you can see over here, as you go from the toe to the heel, you basically, your fracture height varies by 70% along the wellbore. And the same happening with the fracture half length. So it basically varies by 60% along the wellbore. So the problem becomes, and there are several components that go into this. It's a reservoir heterogeneity, one of them. Then it's a stress shadowing effect. So then it's a cluster-to-cluster interaction. Basically, what all those components do is they create a very heterogeneous fracture geometry. So now, for example, when we talk about like, well, let's do one stage optimization. So if we optimize it on the stage at the toe, our fracs will be too, basically our model will show that our fracs are too big. And what we will ended up doing is reducing our tonnages, reducing our simulation intensity. But at the same time, if we take the stage somewhere midway, then it will show us that our frac is too small. So now it will mislead us into the increase in our tonnages and increase in our intensity, which both of those approaches will give us non-optimal completion optimization design. And that's why it's extremely important to perform the full wellbore modeling. And we, by default, running the full wellbore modeling on all our optimization studies, just because the statistics and large number of stages are helping us in terms of to eliminate the detrimental effect of the heterogeneity, either from the reservoir or for the process itself in a way of stress shadow. So then another problem that we're facing with the operators is everybody is switching to the plug and perf technology. Basically, the problem with the plug and perf technology is that we need to have a way of reliably, we need to have a way to reliably predict the perf erosions to try to understand how much proppant each and every perforation is getting. Because basically, if your perforation strategy is not optimized or your cluster strategy is not optimized, then you might end up feeding only few perfs, like few clusters out of 5 or 6 or 7. And as a result, you will get non-uniform fracture geometry, runaway fracks, and all the detrimental effect that we're trying to avoid. So this is the very good example. So this is the example of the perf erosion model. So basically, on the right side, we perform the blind modeling of the perf erosions, and you see clusters over here. You have percent erosion, which basically will demonstrate how much erosion each and every cluster experienced. And on the left side, you can see the results of the dark vision. Dark vision is the ultrasound acoustic tool that you can basically run after your completion job and measure the erosions on each and every perf. And as you can see, like, it's not a perfect match, but it's pretty good match in terms of what we can predict and what actually happening within your wellbore. So, and if you can accurately predict your erosions, then you can accurately optimize your completion designs. Then the next workflow that we developed is going to the ball drop technology. So basically, the main problem with the open hole ball drop is we don't really know where the frac is being initiated within the stage, because typically the stages, or like the stages length are quite significant. So it's anywhere from 25 to like 100 meters. And within that zone, we never know where the frac was initiated and where it entered the formation. So we developed this workflow called FracGuru, which uses stress field calculation and mechanical properties calculation to try to locate those zones of minimum stress within each and every stage. But at the same time, we're trying to quantify the probability of the occurrence of the event. So we can actually, between the different, we try to differentiate between different zones, actually predict where the frac went into the formation. So here on the, where we have a green circles, you can see on the right side, you can see the probability of the occurrence of the frac, and on the left one, you can see the results of the image log that was run within the same well, and as you can see, it correlates fairly well. So then the next problem that we're addressing during this integrated studies is we need to estimate a detrimental effect of the depletion of our nutrients. So basically, what we need to understand is we not only need to understand the spatial distribution of the depletion, or how far it went up, down, left, and right, but we also need to understand the magnitude of the depletion, because as we know, the depletion is not homogeneous, so it will change and vary as we're going from the toe to the heel of the well. So basically, this is one of the key components that needs to be addressed before we can even go into the optimization workflows. And then this is the good demonstration why the proper estimation of depletion and proper history match of the fracs is extremely important. So what you can see over here is the black trajectories are the parent wells, or the first generation well, wells, and underneath it, you can see the map of the depletion. So basically, it demonstrates where depletion went and what's the magnitude of the depletion. So now, if you try to place the frac, put the well in between the two existing wells and pump the frac, you will see that your geometry, your frac geometry, becomes very erratic. And instead of stimulating the virgin rock that you would want to stimulate, basically the majority of your frac is invading the depleted areas from the parent well, and as a result, you're detrimentally affecting your child well frac geometries. Just to talk a little bit more on the standard scope of optimization workflow. So basically, it's a very sophisticated and very thorough type of the optimization. So we typically do the landing depth optimization, well spacing optimization. We do cluster stage spacing optimization, TPM or frac size optimization or frac intensity, preload and pressure sink mitigation strategies, zipper fracking, any hazard analysis, either sour gas or formation water hazard analysis. And we do modeling of all wells and all stages simultaneously to properly account for shadow effects and effects from the reservoir heterogeneity. Then this is a few examples. So now we switch directly into the few examples. So this is the landing depth example, and you can see over here different landing depth strategies. And on the y-axis, you will see the different EORs, or how well your wells will produce. And then you can see that by optimizing your landing depth and how we place the wells within the zone, you can see a quite significant variation in anticipated EORs. So then another example for the well spacing example. So the well spacing is a little bit different. So now when we talk about the well spacing, we start talking about the in terms of NPV or economics, and the economics per well on per well basis and per acreage basis. In our case, it will be section, but whatever land division you might be using, it has to be checked on that land division as well. And the reason why is because the well spacing is directly tied in the development plan and the inventory of the drill locations. So, and as you can see over here, the NPV per well and NPV per section are not necessarily correlate really well, right? So basically what can be perfect for the NPV per well might not necessarily be great for the development plan, and that's why these two things has to be taken into account properly. So, and if we, this particular graph on the x-axis, we have different well spacing going from smaller to larger, and on the y-axis, we have NPV per well. And you can see that if we go with a tighter well spacing, our NPV, both NPVs drop quite significantly. Then at a certain point, they cross over, which will be the sweet spot in our case. But if you go too tight on your well spacing, you will observe the decrease in NPV per well in section due to well interference. And then if you go too sparse on your wells, you will basically start experiencing missed pay and your NPV kind of plateauing, but then there is no way you can go back and put infill wells in between just because there is not enough space. Or even if you could put the infill well, it will be the anticipated production will be very, very bad. So and then another example for the frac intensity. So basically on the x-axis, you have a different TPMs or different intensity going from small to large. And then on the y-axis, you have the EOR or your recoveries. And again, this is for the multi-bench development. So the gray one will be bench one, orange one will be bench two, and then blue one will be combined case. So it's basically average. So as you can see, if you too small on your fracs, you basically again experiencing the missed pay. But then at certain points they're going back to back together, they're overlapping. But then at a certain point they start deviate from each other. And in this case, bench two was pumped first. So what you start seeing is that bench 2 fracs basically occupying the space of what would bench 1 would take within the zone. So, and the problem with this is that you cannot, like, there is only that much you can do with the tonnage and fluids, and you cannot basically you cannot replace 2 fracs with 1 frac with exactly the same efficiency. So as a result, the goal of our work and the goal of our studies is to find this sweet spot over here and basically optimize the tonnage so the both fracs for both well will take exact amount of space that that need to be to maximize the production and maximize the EOR. And then the effect of zipper frac. So this is a very good example. So we have 1 well in the lower zone and 2 wells in the upper zone. And we're pumping exactly same tonnage. We're pumping exactly same intensity. So it's exactly same design for all 3 wells in all 3 cases. But depending on in which sequence we pump those wells, you can see that we can either maintain our fracs within the zone, or we can completely push them out of the zone. So basically, the zipper fracking can be your best friend or can be your worst enemy. And that's why it's extremely important to predict and model it properly to understand where your fracture geometry is preferentially going and how we can alter it if needed. So in the new piece of science that we recently introduced into the integrated workflows is the quantitative flowback data analysis. So basically what it is, it's similar to RTA technique that being used to analyze the flowback data, or it's basically the completion fluid and completion water production after we pumped our well and we're going into the cleanup flow, and to analyze this data and derive the fracture properties. So basically, the key benefit of it is that flowback data analysis can validate average frac parameters estimated from frac modeling, and we don't need to wait for the long-term production data. So basically, we can answer this question, how efficient our fracs was, within a couple of days after the flowback data was acquired and after the flowback was started. And the benefits of including flowback analysis in integrated studies is basically it's a limited data requirements. Typically, we have enough data after 2 days or anywhere from 2 days to 2 weeks, depending on which formation we're working with. There is no additional field cost, so you have to flow back your well. You have to acquire your data no matter what. So the data is already there. So basically, and what we can extract from the flowback is we can extract the mobile fracture volume, we can extract our fracture conductivity, we can extract our fracture half length matrix, or SRV permeability. So basically, we can quantify right after we completed the well how good of a frac we just pumped. Then just for the conclusions and achieved results. So basically, after we performed the studies and applied it in the field, we don't see any detrimental frac hits. We don't see underperforming child wells. We don't see damaged parent wells. We actually see 10% increase in production on the parent wells, which we don't necessarily think is a good thing. We think it is a damage. It's just we're not properly quantifying it. And of course, since we optimize in for economics and all the NPVs, we don't see overstimulated reservoirs or capex overruns. So basically, on average, we can achieve 20% decrease in completion costs and 30% increase in child well production. And a lot of people asking how accurate those workflows are. Basically, it all depends how much effort and how much time you want to spend modeling those processes and modeling your reservoir along with your completion designs and like the dynamic simulation or production simulation. So basically, on average, you can achieve 8% accuracy or 8% difference on the 90 days production between modeled and actual production. If you take it, like if you look at the average pad or average well within the area, but then it will require a lot of effort. It will require a lot of inputs from the all teams, like the whole multidisciplinary team. Right? So it will require G&G input, it will require engineering input, and of course completions team as well. So then, just to show you, this is the last topic that I'd like to talk about. So basically, exactly the same workflow, but very simplified. Can be applied in a real time. So we call it PumpZilla. So basically, the whole idea behind it is we already have the completion pumping data. We have pressure rate from our pumping company. We have pressure data from monitor wells. And we can build a quick geomechanics and reservoir model, throw it into the PumpZilla workflow in the real time, and we can basically optimize our completion design as we pump. And the same goal, right? So instead of doing the integrated study prior to the completed the well, we can basically try to solve the problem of the exactly same problem as we stated at the very beginning, but in the real time fashion. And then this is one of the examples that we run. For one of the operators. So basically, what you can see over here, it's a gun bar. Sorry, it's a top view. The blue well is the well that we're actually completing, and then the nearby well is the monitor well. So basically, the whole idea behind it is what we're trying to do is we're trying to recreate the fracture geometries as we pump, right? So and then if we can do that in the real time, and we can actually recreate the fracture geometry, and we can measure where the proppant went, then we can differentiate between the no frac heat, hydraulic heat, and detrimental heat. And we all know that hydraulic heat's happening everywhere. They're okay. Industry got used to it. But what we want to avoid detrimental frac heat. And this is the very good example of how we can do it. So basically, as we were pumping, we were seeing a bunch of hydraulic heats, which is okay, just water flooding the depleted area. Then all of a sudden, we started seeing detrimental heats. And what we did is we dropped our intensity and heats disappeared, and then we resumed it back to where it's supposed to be. But then basically detrimental heats occurred again. So what we did is our conclusion was that basically our design is too big for that particular area and that particular well spacing. So we reduced the intensity and proceeded for the half of the well with a slightly reduced intensity, and our detrimental heats disappeared, and everything was good. Then all of a sudden we started seeing detrimental heats again. So we reduced the intensity, heats disappeared, we resumed it back, and we never seen the detrimental heats again for the remainder of the well. So basically, the conclusions from this piece of work was that over here at the mid stages of the well, we clearly identified that our tonnages were too big and our intensity was too significant for the given configuration and geometry. But then over here, closer to the heel, we basically hit just some conduit or fault or some geological feature that basically transported the problem from one well to another. And as a result, we did not reduce the intensity for the remainder of the wells. But if we wouldn't apply this work, what we would do is we basically reduce it, and we would understimulate the whole heel area of this well. And I guess on this one, I'll go to the questions. Thank you so much, guys, for your time, and thank you for having us today.